We looked at one of the very popular unsupervised technique in ML, namely that of clustering. So basic principle behind clustering is that we take a bunch of data points which behave similar to others in its neighborhood and try to form clusters of similar behavior and identify such clusters of data points which are similar in behavior and which are different from the data points in other clusters. So the basic idea is within a cluster we would like to increase similarity in terms of increase the similarity, and between different clusters we would like to have maximum dissimilarity. In a sense, we should try to decrease the similarity between across the clusters. So when you say clustering, one of the key problems we have is we don't a priori have a clear notion of what is the number of clusters we can expect, namely K. So that is why we usually have a set of techniques to determine what would be a kind of right size of the number of clusters. But what happens is once you know what a K is, we have techniques for actually identifying the kind of clusters in the original data, like K-means cluster. So what K-means clustering does is it takes the original data, it can divide the entire data into K clusters. So let us look at briefly what K-means clustering does. K-means clustering is basically, if you see from the input perspective, it takes the original raw data, which is unlabeled, there is no output variable. In that sense, it is an unsupervised algorithm. Only thing we're trying to find out is a pattern, which is in form of what is the collection of, what you can say, cohesive groups of data items which are high on cohesion and coupling between each other and which have very distinct characteristics from the data in the other clusters. So in terms of the K-means clustering, it is a very simple idea. The idea is that you first determine K or fix K. K is given as input to K-means clustering. So if you're talking about 3 means, you're talking about 3 as given input to the K-means algorithm. If you talk about 2 means, 2 is given as an input to the algorithm. So K is something which is not determined by the K-means, but K is fixed before the K-means clustering algorithm. So let's take random points as inputs. Now let us say we have K equal to 2. We're talking about forming 2 clusters from here. So what we do is we start with first randomly taking 2 points and designate them as centroids. Let's take 2 random points among the original points as centroids. Because we're talking about 2 clusters, we have 2 centroids to start with. Now, once we have chosen the initial 2 centroids, for each point, you try to find out which is the nearest centroid. And based on that, you give that number 1 or 2. If you call the centroid 1, this centroid is 2. So at the end of it, all points will have some name, right? 1, 1, 1, this will probably be 2, 2, 2, 2, 1, 1, 1, 2, like this. So at the end of this step, all the points in the input will have one of the centroids associated with it. Done? So now we have gone with the initial assumption of 2 centroids. We've taken the points which are closest to 2 as belonging to cluster number 2, all the points belonging to closest to point number 1 belonging to cluster number 1. Now comes the magic. Now if you compute the centroid of all the points with the label 1 and compute the centroid of all the points with the label 2, are they going to be the same as the original point? Here is the question. The question is, if you take the centroid of all the points which are labeled 1, and centroid of all the points are labeled 2. This is the same as the original 1 and 2 points. The answer is no, because at that time we are taking a random choice of points. Now we take the actual centroid and we say 1 dash, 2 dash. Say this is probably the centroid. So we'll say that this 1 dash is the new centroid. Say this is 2 dash. And now we have two new centroids, which are the actual centroids of the points identified by the two clusters earlier. Now we have two new centroids, 1 dash and 2 dash, right? Now we can go back and repeat the same process with again all the points in the original data. Take the original set of all points, take the new centroids 1 dash, 2 dash, find out which point is nearest to 1 dash or 2 dash. If it is nearer to 1 dash, rename it as cluster 1. If it is nearer to 2 dash, rename it as cluster 2. So now you have probably some rearrangement. This may go into 2, this may go into 2, and this may remain 1. That's fine. So some points will move from one cluster to the other. Now what happens is we have changed the cluster formation to a new formation, right? Now again we compute the centroid of the new assignment. We find out the new centroids of the revised cluster assignments. And we find out that there is 1 dash dash, 2 dash dash. Then, now again we repeat the same problem with assigning the nearest cluster number to the nearest centroid to which the corresponding point is in the next loop, and continue this loop forever till you find that there is no relabeling happening. So when no relabeling happens means we are talking about all the assignment of clusters of cluster 1 or cluster 2 is stagnant, means centroids are no more going to change, and we see that this procedure can come out, and we now have two stable clusters which have distinct assignments of the points corresponding to each of the clusters. So same thing we will want to repeat. If k is made 3, we can do with 3 centroids. If k is 4, we do with 4 centroids. If k is 5, we do with 5 centroids. But the beauty of this is that we can let the data itself decide where to stop by just checking the point of no relabeling happening at that iteration. So once you have the stage, then we can stop and we ultimately get a proper assignment of two clusters, cluster 1 and cluster 2, at the end of it, where it is stable and there is no relabeling happening. So k-means clustering in that sense is a powerful but simple technique for identifying clusters within the original raw input data without having to explicitly label any data. And the beauty of this is that we can actually also iterate over different values of k, and by different kinds of inspection mechanisms, either by looking at relative distortion between the different cluster sizes, or by looking at whether one cluster is very sparse, other is very dense. We can try to find out which is the right k for our purpose, and we can freeze that as the right number of clusters for the original data. But this definitely is a disadvantage, not having a mechanism to actually determine the right k for your data. In fact, in history or in machine learning, there is no scientifically proven technique for determining the right k. We will look at some techniques for determining k, but the basic idea here is that we do not want to constrain ourselves to any predetermined notion of a scientific method to approach k, but instead do some kind of an iterative approach to k and find out which is the best value of k. But key important thing is also when we say nearest centroid, then there is a point, say P, and say C0 is C1. You need to have a notion of the distance. So the nearest distance notion also plays a very important role in determining how and what cluster you will assign to a particular point. So we look at different distance measures in a different field. Our distance measures are equally important when you're describing clustering assignments in k-means clustering.